Welcome to 38th lecture in the course of Industrial Engineering and Operations Research. We are discussing now the operations research, and in the operations research, I am talking about linear programming problem, and we discussed about simplex method. We also told about dual problems. That means, if you have got a problem, then you have a dual of it. Okay. That means, suppose you are maximizing, this becomes the minimization. Okay. So, we told that how to obtain a dual problem, that is what it is this one. So, today we are going to discuss about unit worth of resource. You know that if you have got a primal problem and if you convert to dual problem, then what you can do, that dual variables will denote the unit worth of resource of the constraints of the primal problem. So, that is what is the unit worth of resource. You know, already I talked about unit worth of resource. Suppose you have got a objective function z, say 5x1 plus 6x2 plus 3x3 like that, and then you have got some constraints, maybe x1 plus x2 plus x3 is smaller than, suppose I have to maximize, and we say that here it is smaller than 10, and maybe x1 plus 2x2 is also smaller than 12. Then suppose first constraint, its worth. So, its worth is how much, that suppose I increase it by 1 unit, then how much the objective function will increase. That means, I make 10 is equal to 11, then my optimum value will increase how much. So, that is called the worth of the constraint. Okay. So, that is this one, but we can have that good idea from the primal dual type of problems. So, let us discuss that point we will discuss. Okay. Suppose now we have primal problem. So, let me write primal problem as maximize z is equal to 1 to n Cj xj. There should not be very much difficulty for you to understand that I am writing C1 x1 plus C2 x2 plus Cn xn. Okay. So, you understand the compact notations. Okay. Generally, most of the time, most of the students who are not mathematically strong, they prefer that I should write the full expression, but you know that we have to, sometimes it becomes difficult. So, that is why you learn the compact notation j is equal to 1 to n Cj xj is equal to C1 x1 C2 x2 plus Cn xn, and such that j is equal to 1 to n Aij xj is smaller than Bi, I is equal to 1 to m. Understand that these are the m equations. So, these are m constraints, and each one there is a expression. So, basically there it is basically a matrix whose row is m and column is n. So, it can be written in the form of matrix, and this is the thing. So, each one is one constraint. Okay. And xj is greater or equal to 0, j is equal to 1 to n. So, xj is the design variable. Now, if I have given this primal, there is something called the standard primal also. We can convert this problem into standard primal. How we can convert? Maximize z is equal to this much. So, you say maximize z is equal to j is equal to 1 to n Cj xj, no change here, but such that this was smaller than or equal to constraint, but you make into equality constraint, then it becomes in the standard form. So, it becomes j is equal to 1 to n Aij xj plus Si is equal to Bi, and this is I is equal to 1 to m. So, therefore, you have got m equations. In each equations, of course, there are a n variable, and we introduced Si also extra. This is called slack variable. Okay, slack variable. So, this is what in standard form we have written, and this is also our convention that we will consider that Bi is positive. If Bi is not Positive, you can always multiply it by -1 whole equation. So, it will become positive. It is very possible that if you have x plus y is equal to -5, multiply whole thing by -1 and say minus x minus y is equal to 5. So, it is not a difficult thing. And xj is greater than 0, j is equal to 1 to n, and si is greater or equal to 0, I is equal to 1 to m, because m slack variables we have added. So, this becomes a standard problem. Now, if it has become a standard primal, its dual can be obtained very nicely. Maximize becomes minimize, maximize goes to minimize, and z becomes w, minimize w, another function, and corresponding to each constraint I have got one variable. In fact, that variable denotes a type of unit worth of resource. When we solve that problem, optimize that, it will give the unit worth of resource or dual variable. So, associated with each constraint, there is one variable y. So, therefore, w sigma I is equal to 1 to m biy. Simply we say biy. Okay. So, that is how that we obtain that objective function, and such that now how to obtain constraints. There are n variables. So, corresponding to each one there will be constraints. Now, constraints are now how many variables are there? N variable in the original problem, but I have added slack variables also. So, they become something like extra also. So, n plus m variable. So, what happens that if we solve in a systematic way with this, with minimization, there will be greater than sign, and we have like that sigma I is equal to 1 to m sigma aij yi. Why yi? Because there are m constraint, each one will be multiplied. Say for example, x1's thing will be that pay attention to x1. So, a11 and this will be y1 plus a21, okay, and then this will be y2, okay, like that, and this will become that finally like that it will go, and this will be like that, last one is an1 like that. So, this is how that you will get sigma I is equal to 1 to m aij yi greater than Cj, okay, because Cj is the corresponding coefficient. Now, even for this variable you have to worry. So, therefore, what happens? This will give Si, first one, only it is in this one, in no other constraint this is one, because in each constraint we have added a separate slack variable. So, it is only one, suppose S1. So, with this S1 there will be, you will associate y1 first constraint. So, you will say y1, but in the objective function it is not there to the 0. So, it will be y1 greater than 0. So, that means you will get y1 greater than 0, those type of things you will get here. So, that is how that you get y I equal greater than 0. That is how that from standard problem to dual problem it has come. Otherwise, you have to remember by your own way that see maximization becomes minimization, and these are smaller than type of constraints. So, they becomes greater than type of constraints. Up to this much you can do. If there is a quality constraint, then you have to worry that what happens if there is a quality constraint here, even then there will be greater than or equal to sign. Only thing that particular variable associated with that constraint will become unrestricted. Okay. So, that type of thing is there. Anyway, so now an example that how I am talking about these numbers. So, let us say suppose the primal is maximized z is equal to 5x1 plus 7x2 plus 4x3 such that x1 plus 2x2 plus x3 is smaller or equal to 5, 2x1 minus x2 plus 3x3 is smaller or equal to 4, x1, x2, x3 is greater or equal to 0. So, if we compare that as such with our notations, this is C1 will be 5 because this is coefficient C1, C2 will be 7, C3 will be 4, and B1 will be what? B1 will be 5, B2 will be 4, and A11 will be what? 1, because this is the first A12 means first constraint, second variable A12 will be 2, A13 will be 1. These are the matrix elements A21 2, A22 minus 1, A23 3, m is equal to 2, that means number of constraints is equal to 2 and n is equal to 3, n is equal to variable. So, dual will be what? Minimize B1 Y1 because there are 2 B na B1 B2. So, therefore, B1 Y1 B2 Y2, B1 means 5 Y1 plus 4 Y2. So, you see 5 Y1 plus 4 Y2 subject to I is equal to 1 to 2. Now, it becomes Aij Yi we have written. So, that means j is equal to 1 to n. Okay. So, that means that this becomes basically A1j Y1, A2j Y2 like that, and it is equal to Cj. Okay. So, I is equal to 1 to 2. So, j is equal to, suppose first Y1 Y2 is greater than 0. Okay. So, if you expand that, so first becomes A11 Y1, A11 like transpose type of thing, A21 Y2. That means in this row A11 means 1, A21 Y2. A21 is also a coefficient of x2, but in the second constraint, that is why there is Y2. A11 is a coefficient of x1, but in the first constraint, and this should be greater than or equal to C1 coefficient. Here smaller than sign will not be there, with minimization greater than, and you get Y1 plus 2 Y2. Similarly, A12 Y1, now you are writing the second constraint corresponding to second variable means x2. So, it is x2's coefficient in the first constraint. So, that is why A12 Y1, and this is x2's coefficient in the second constraint, that is why it is A22, and this is equal to greater or equal to C2, and then you get 2 Y1 minus Y2 greater than this one. Similarly, you get A13 Y1 plus you get A23 Y2, and it is greater or equal to C3, then you get Y1 plus 3 Y2 greater or equal to 12. So, that much you have done. Okay, you got this one. So, what we are seeing that you see variable n and resource m were there in primal problem, and profit per unit variable j is Cj, that is why we Cj Xj, that means it is maximized. So, we are maximizing profit, let us say. So, Cj Xj. Then what is this A11 etc.? This is consumption of resource I per unit of variable j is Aij, consumption of resource I. So, this is first resource, okay, A11, that means first resource, and it is in the first resource used for making 1 unit of this one. Similarly, first resource used for making 1 unit of x2. This is first A13 because A13 is multiplied by this one A13 x3. So, that is why that you know first resource, but used for making this one. So, therefore, understand that consumption of resource I per unit of variable j is Aij, this much you are doing consumption. Okay. So, therefore, now from property 2 we said, we already said that dual property in the previous lecture, and we said z is equal to at any iteration j is equal to 1 to n Cj Xj, that means profit is smaller or equal to I is equal to 1 to m Biyi is equal to w. Okay. So, this is equal to this one, and equality will hold when you have reached the optimum. That means, when you have reached the optimum, it is balanced type of thing, then whatever profit you are making is worth of resource. Okay. As long as profit is less than something worth of the resource, that means there is a scope to optimize. So, that is why this is this one. So, let us see that, let us interpret in a very simple way. Suppose we consider that profit is in terms of money. So, we say that z unit is money, z unit is money. So, money is equal to j is equal to 1 to n, and this will be profit per unit of variable j, because Cj is the profit per unit of variable j, and this is Xj is the quantity of variable j. So, this is how that you got. At optimum, money will be equal to sigma I is equal to 1 to m quantity of resource I. What is quantity of resource I? Is basically BI. You can say this is the quantity you have got, and unit worth of resource I is equal to YI. That means this is the worth of the resource. That means, and this equal to, hence YI is equal to worth per unit of resource I. It is also called dual price. It is also called shadow price. It is also called simplex multiplier. It is simply called unit worth of resource. Okay, that is what interpretation of YEI is there. So you understand that in one problem, you whatever you have got the units, in the second problem it is basically the worth of the resource. Okay, so that is what. Now here objective this is, so we said that property 1, already we said that as a property 1. Let me just go to that from property 2. Okay, so this is property 1 basically, from property 1. Any one property you have to say 1 and say other is 1. So from property 1, objective coefficient of xj is equal to sigma I is equal to 1 to m sigma ij yi minus cj. Why? Because this property was given to you that at any simplex iteration of the primal or the dual, objective coefficient of variable j in one problem is equal to left hand side minus right hand side of constraint j in the other problem. So suppose I have got the coefficient xj. So in the xj is that fine that it is a coefficient in the primal problem, but in the jth constraint, so in this one left hand side minus, so in dual problem this will be I is equal to 1 to m sigma aij yi minus cj, because that's how we make the constraint in dual problem. Okay, so here it is xj, but in dual problem how we will make the constraint? We have already seen that we are making sigma ij yi. Okay, we are making I is equal to 1 to m. We are paying attention to jth variable. So we are putting each constraint aij into yi. Yi is the quantity used in this one, and this is equal to j, that can aij yi, and then it is equal to minus cj. Okay, so we are associating with this one cj. That means we are putting greater than cj, that variable used to come. So we took it other side and we said this is this one. So this type of from property 1 we got, and we already noticed that because cj is the profit, so therefore this must be some other thing, loss or whatever you say the value of that. So we can interpret as objective function denotes profit per unit, therefore sigma aij yj is equal to money per unit, because you are objective coefficient and this dimensionally matching should be there. So this is money per unit, and cj is equal to profit per unit. So aij must be amount of resource I used by variable j, hence y must be some cost. Opposite of profit is the cost. So we say it may not be, we may not be paying that cost physically. That means businessman may not be paying that cost. Okay, he just, but he is understanding that point. So it is called imputed cost per unit of resource I. So yi is also called unit worth of resource, or it is also called imputed cost of. What is imputed cost? This terminology comes in finance, etc. And imputed cost, also known as an implicit cost or implied cost or opportunity cost, represents the value of a resource that is used by a business but not directly paid for. That means you are accounting, but it is not like that. You are utilizing some worker, and worker is making something product. So naturally there is a imputed cost of that worker, based on that they make, but it may not be that exact amount you may not be paying to, that is different thing, but it is accounted. So sigma I is equal to 1 to m aij yi is greater or implies that sigma I is equal to 1 to m Aij Yi is imputed cost of all the resources in making product J. So, product J is we are making product J in this is the thing. So, this is sigma Ij is basically money per unit. So, this is product means per unit wise. Okay. So, suppose because suppose you are making a product J. Okay. So, you are using so many resources, m resources are there. So, Yi is the this one, and you are using Aij, that means Aij quantity for making 1 unit. So, you say Aij into Yi, something like you can, and you can say A1, suppose resource 1, so A11, A11. So, suppose you can say that here resource product 1. So, I am concentrating on product 1. So, A11 Y1, but then A21 Y2, A31 Y3. Okay. That means 1 is common. Okay. But A11 means first resource, and it is you know this one. That means resource used A11. So, this is the thing. So, pay attention to sigma I is equal to 1 to m Aij Yi minus Cj. So, if you have this is what imputed cost and this is Cj is the profit coefficient. If it is negative, we can increase Xj. Okay. That if it is negative, then we should increase, otherwise we should not increase. So, you might have seen that the Z row in the simplex table I told as per the book of Taha, that is basically imputed cost table we can say, sorry, imputed cost row we can say, but we have been telling Z row, but that is the thing, and we used to see this one. So, there is a logic why if it is negative, then we can increase Xj. There is a logic in enhancing the production as long as the imputed cost of used resource for product J is smaller than profit per unit of product J. Okay. So, you are getting more profit. So, therefore, you increase that, but as soon as imputed cost is more, then you should not, because then cost is more, why should you utilize that resource too much. Okay. So, that is what this one. So, there is a this one. So, interpretation is that we can even say that Zj is equal to I is equal to 1 to m Aij Yi, we can use like that symbol. Okay. People use that, and then say Zj minus Cj is objective coefficient of Xj in the simplex table. In some books they write it, call it a reduced cost, and they write it a separate type of and they say that, and Cj is already known, so again and again they calculate. But if you do Gauss-Jordan method, it is what I told Z row, it is simply that Zj minus Cj. So, therefore, you do not have to take much tension about that, it is basically the same thing, but I have told if you just refer other books of the linear programming other than Taha, then you may get these notations quite frequently. Okay. So, now we will be discussing other things. Okay. So, let us take one example. Suppose I have got maximized Z is equal to 5x1 plus 4x2 plus 30x3 plus 25x4 plus 20x5 plus 10x6. There are 6 design variables, and subject to, there is only one constraint here, 5x1 plus 2x2 plus x3 plus x4 plus x5 plus 2x6 is smaller than 10, and all of these things are positive, all decision variables are means positive or 0. So, I can make a dual form of this. If I make the dual form, I know there are 6 variables in the dual form, there will be 6 constraints, and here there is only one constraint. So, in the dual form there will be one variable only, and how we make that quickly by doing in rough work, I just wrote y here, associated with this constraint is one variable y, that is dual variable, or you can call the unit worth of resource of that variable, whatever you want to call, you call simplex multiplier. So, therefore, maximize becomes minimize, maximize Z, so minimize W, and is equal to y. So, how much? 10 this resource quantity is 10, so 10y. So therefore minimize 10y. You minimize the worth of the resource, you minimize the total worth of resource, because y is the worth per unit. And subject to how much? So subject to that, you just pay attention to first variable. First variable uses 5 quantity per unit. So 5 into y, okay, that means worth is y, okay, of the worth. So 5y greater or equal to 50, smaller than becomes greater than, because coefficient of x1 is this one 50. Then 2y greater or equal to 40, then y greater or equal to 30, y greater or equal to 25, y greater or equal to 20, 2y greater or equal to 10, and then you say that y greater or equal to 0, that is the thing it will come. How y greater than 0 is equal to come? You just have to remember that it is like that, okay. Suppose smaller than, then otherwise if you want to be very particular, you can say that, okay, I can convert it into standard problem and say plus s is equal to 10, then corresponding to this s also you write one variable. So coefficient is here is y and here there is 0s. So therefore you say y greater or equal to 0, and then say this is the thing y unrestricted. So whatever form you know, remember, you remember all things are equivalent. One method you have to understand. So now it is, we have written this type of problem. If you want to solve this, we can solve it graphically also. I can just show you that w y. So these are the constraints. Y must be, let me just see, y greater than 5, y greater than 10, is it not? Y greater than 20, y greater than 25, y greater than 30, okay. And so it is all these. So other constraints become redundant. Everything has to be satisfied together. That means y must be greater than 30, and we have to minimize. So feasible region for y is bounded by y greater than 30, as it is the tightest bound. Therefore the feasible region includes all values of y greater than 30. Y greater than 10 will not be applicable, because y greater than 30 will not be satisfied. But if y is greater than 30, then y is also greater than 10. So objective function is w is equal to 10y. So to minimize w, we need to take the smallest possible value of y within the feasible region, that is y is equal to 30. Hence minimum is equal to w is equal to 10 into 30, that means 300. So at the optimum, the objective value of dual and corresponding primal problem is equal. Hence maximum value of z is equal to 300. Okay. So you got maximum value of z is equal to 300. Now let us see that dual constraint. Pay attention to dual constraint. So dual constraint was I pay. Suppose we have put this constraint, previous one, 5y greater than 50, and I have got these things. So 5y. So 5y, 5 into 30, 150 greater than 50. So it is not tight, okay, because 150 means you are much ahead than 50. So not tight, okay. 2y, 2 into 30, 60 into 40, not tight, okay. That means there is no problem because of this constraint. So it's a unit worth of this one resource will be 0. Suppose it is like that, not tight, so therefore x1 will be 0. This is x2 is equal to 0, because its worth will be 0. In one problem, whatever is the variable, in the second it becomes worth, okay. So if constraint is not tight, means if constraint is not the border case, that means, okay, suppose I am already getting 5y greater than 50, okay, that means, and it is much this one more than 50. So I am not bothered about that constraint, okay, because if I am bothered about this thing, if your constraint is y greater than, suppose let us say 30, and your value is 50, you are safe, okay. That is what, no problem about, as if that constraint is not there. So this is also 0. Y is equal to 30, so 30 is tight, therefore x3 is not equal to 0, because y is ditto 30, okay, and constraint was y greater than 30. You are at the border case, that means moment you reduce a bit, then you are gone, okay. That is what here 5y was 150. So that means y can be reduced also. So this is y greater than 30. So therefore it is tight constraint. That means equality holds good. So x3 will not be equal to 0. It may have some worth. Okay, that is okay. Of course, some cases worth can be 0 also, but generally you cannot conclude. And here y is equal to 30. 30 greater than 25. So not tight. So that means this resource is abundant, because I have got some value which is much more than safe zone. Y is equal to 25 is here, but I am here. So I have a lot of margin. So I need not worry. I will not collide with this constraint. Even if I move a little bit here and there, this constraint, as if it is not there, I am not touching it. Okay, so that is why that it becomes like that. So x4 is equal to 0. Similarly, y is equal to 30. 30 greater than 20, not tight constraint. Okay, so x5 is equal to 0. 2y is equal to 60. My value is giving 60 and it is 10. So it means this one means we are much safe. Okay, that means here it says that y must be greater than 10, but I must getting that here 2y must be greater than 10. Okay, in fact this is y is greater than 2y greater than 10. Okay, so this is here it is I think y greater than 5, rather y greater than 5. Okay, 2y greater than 10 means y greater than 5. So suppose my value is here and constraint is there. So lot of free zone is there. That means if somebody disturbs this constraint, brings towards that thing, then also you are safe. So that's why this constraint's value is not there. As if this constraint was not there. Okay, only as if only y greater than 30 is there. That type of situation you are facing. So that's why we said that here x6 will be 0. So therefore in primal problem only x3 will be non-zero, all other things, and I already know the profit. So I can calculate the x3. So I can calculate, we can calculate, since only the constraint y greater than 30 is tight, or only that constraint is active, we also say active, because the value is 30 and constraint is this thing, we are just at the border. Okay, suppose I would have got y is equal to 50, then even that was not active. Okay, of course if I get y is equal to 29, then it will not be accepted. Okay, so the corresponding primal variable x3 is positive, and now from the primal constraint this is equal to 10. So therefore 5 into this one, so it is equal to, you have got this one. So we can also say that x3 is equal to 10, or else we can say that variable maximum value of z is equal to 300, and 300 means this much. Okay, so 330. So therefore x3 was okay, so maximize z is equal to 30. So that means you can obtain x3 is equal to 10, then your profit will be this thing. Or you can say from constraint also that if this constraint is okay y, and this is since y is non-zero, so this is equal to 10. So by that also you can find out whatever you want to find out. So optimal solution in the primal problem will be this much. So you know, see, I have got so many. So otherwise this primal problem I could not have been able to solve graphically, because there are so many variables. I converted into dual form, and from dual form I got, and then I could calculate these values also, because I could find out this much only, and this is what you have got. Okay, so this is equal to x3 is equal to, we got 10. Okay, because this is equal to that one. And here let me just tell one more thing. Okay, so this is equal to 10. Now, so unit worth of resource, as y is equal to 30, then unit worth of resource of constraint this much, 5x1 is smaller than 10 is 30. This means if the change, if RHS right hand side changes to 11, then the objective function will increase by 30, because you worth of resource. So this is equal to z is equal to 50. You can see also that when x3 is equal to 10, then z is equal to 30 into 10, that means 300. But if I make it x3 11, then z is equal to 30 into 11, that means 330. Okay, so this is how that it has come. Okay, like that, and then it will be this one. So this is the unit one. So solution will be x3 is equal to 11 and z will be 330. Okay. So, this is the thing. So, this much only for today, and then we will continue the discussion in the next class. Thank you very much. Okay, thank you.